Okay, so we're looking at chapter 2, which deals with digital switches and signals. We talked about the different names or nomenclature that we use. Everybody okay? What did we talk about here? We talked about cycle. Everybody okay with a cycle? Everybody okay with a period? So what's the period? Yeah, the time it takes to come up one cycle. We talked about frequency. What's the frequency? It's the rate of the cycles. Okay. So frequency is the rate of the cycles measured in cycles per second. So when you say what is frequency, you can't say cycles per second, right? Because we have a frequency for our house. We have for our life, right? You understand? For years. So when we talk about frequency, we're talking about electrical frequency, which is measured in cycles per second, or we have another name that stands for cycles per second. And what is that name? Starts with H. Hertz. Yeah, so Hertz is a name, and that's what you'll hear most often is Hertz, even though it's in cycles per second. So Alabama Power generates 60 Hertz. So their frequency is 60 cycles per second. But they generate a sine wave. They don't generate a pulse waveform. Even though we can use it for timing. If you've got any clocks that lose their time when power goes out, then odds are they're timing off Alabama Power. Because that 60 cycles is basically, it's almost perfect. Because because of all the different devices that are frequency, that require or depend on that thing being 60 cycles. The voltage can change, but the frequency don't. So, which is pretty neat. So yeah, if you got a clock that loses time when power goes off, then odds are it's what? Odds are it's timing off Alabama Power. Well, that's got an internal clock. You know, we do have clocks like this right here. So this is timing off my watch. Off my cell phone. But it still keeps time even when it loses contact with my cell phone. So it's got a crystal oscillator in there, probably quartz crystal. We're going to talk about some more terms on this guy right here. We can go ahead and look at some right now. So we give the names the edges. So we have an edge right here, and you can't really see it. So right here at this time right here. So right at this time right here, we have an edge there, and the term for this edge is since it's going from up here at 5 volts down, so that's the direction. This is referred to as the falling edge. And what do you think we call this? Rising. If I can spell rising. Yeah, I got it. I was trying to put raising. It's the rising edge. And we'll talk about later on leading edge and trailing edges. Leading edge and trailing edge is an arbitrary term because it depends on what you're looking for. What initiates something or what something times off of. So if it times off the low going edge, that would be the leading edge. If it times off the high going edge, that would be the leading edge. So, but the rising edge will always be the transition from a zero to a zero, not 0 to a 1, from a low to a high. So we call this too. We call this a low. And guess what we call this? Yeah, we call this a high. So those things have different terms. This would be true in the logic that we're studying. The logic that we're studying is a logic called transistor logic. We'll explain how I got that name as we go through the class. And so if you ever heard of TTL, that's what TTL is. Transistor logic. Transistor logic, a high and a 1 are the same thing. And a low and a 0 are the same thing. But if you get into like ECL logic, guess what? The more negative voltage is the high, and the more positive voltage. If you ever heard of RS-232, which has been replaced by RS-488, I think, which is what we use a lot in PLCs. The negative is the 1. So you can't say a high is always a 1 and a low is always a 0. You can't say that because it all depends on the technology that you're dealing with. Does that make sense? All you got to do is have 2 representations. So to represent binary, all we need is two things, right? One of them is going to represent a 1, and the other one's going to represent a 0. A TTL, a ground, this is not a nothing, so we switch it to ground or common for a 0, and we switch up here for a 1. So TTL, that's true. Anything else? Let's see. So the period, the frequency, and later on we'll talk about pulse width, which we're not going to do right now. We okay on frequency? So frequency and time are inversely proportional to each other. So if frequency goes up, time goes down, right? You understand? Or the period goes down. If frequency goes down, the period goes up. So and they're the inverse of each other. So anytime we want to know the inverse, we do we call what we take the reciprocal. Yeah, and like I said, we do that so much that a scientific calculator has a reciprocal key on it. You'll see people when they're new to it, they wanted 1 divided by, when they can just hit 1 key and it will do the reciprocal for you. Everybody okay on mega, kilo, all these guys? So y'all did this in intro, right? We talked about serial, talked about some of the technologies that use serial. The 2 predominant that we have now are, of course, Ethernet. Well, ISDN, you won't see this much anymore. This is a technology that we use for the old phone modems. Y'all remember those? Yeah, so the V.90 modem was the last version they came up with. DSL, of course, a lot of y'all got cable. So all the information now going over that cable is digital. For years it was analog, but now all of it's digital. All that's digital information. So if you didn't have that box out there on your house and you tried to capture that information, it wouldn't be nothing, right? These are the different versions of Ethernet. Also, these are the different versions of what we call Wi-Fi. Wi-Fi just hit this mark right here, by the way. It's been, and then cable and DSL. Digital serial link. We talked about synchronous serial, asynchronous serial. You okay? What's the advantage of synchronous serial? Well, it's time. It's synchronous, right? It would be the fastest we could send data. What's the advantage of the asynchronous, which is what most stuff is in? Yeah, it's a lot cheaper. Saves a lot of wires. Saves a lot of electronics too. We talked about differential. This has been the rebirth of serial right here, where we got a circuit over here that only lets stuff that's moving in opposite direction comes through. So basically, it eliminates electromagnetic interference. All right. And you can tell that when you look at the pinout for USB, you'll see one called +5, you'll see one +5 or common, and then they'll say a plus minus. And it's not plus DC and it's minus DC. Plus is the uninverted signal and minus is the inverted. So there it's a symbol. It's not a sign. It's a symbol when you get into these differential interfaces. We looked at parallel. Of course, the advantage of parallel is fast. The problem with parallel is very, very expensive. So I can afford to do parallel inside my computer, right? On what we call our motherboard in there. So most of the communication on the motherboard between the motherboard and the memory and everything, the chipset and everything's in parallel. When we start hitting peripherals, you know what a peripheral is? Come on, guys. Y'all been dealing with computers a long time. I'm sure y'all heard the term peripheral. A peripheral is anything that communicates with the computer through a port. So what we have is we have our inside the computer, we got things moving in gigahertz, right? You understand? When it hits the outside world, we don't move in gigahertz. I mean, there's no way in the world I could type at gigahertz on this keyboard. So I'm up here typing. You see some people do this, trying to get information into a machine that's running at 2 or 3 gigahertz. So what we do to compensate for the speed differential and also to be able to assign ports address is that we have devices called portals. Portals, yeah. So basically, the makeup of a computer is we've got everything inside. It's really, really neat. So what would be inside the computer? Well, of course, we're going to have the processor, right? Where did I put my blank slider? Undoubtedly, I didn't put one. Oh, I keep hitting from the beginning. So the basic block diagram of a computer, there's a lot more to it, guys, but we got the microprocessor, or the processor, CPU, different term. And then we've got these buses. We talked about 2 of them, right? The data bus and the address bus. The data bus is what we call a bidirectional bus. Now, usually when we have a lot of wires that serve the same or similar function, we draw them in what we call a bus structure. And then this goes out here and connects to, the data bus goes out here and connects to the memory in the computer. And we have 2 types of memory. We have RAM and we have ROM. Anybody know the difference? Yeah, but why do we need that? Why do we need that? Well, you can think about ROM as being the autonomous nervous system that we have. So when we're born, we've got programs in our brain. What do we already know how to do? The instant we're born, we know how to do things. What can we do? We can cry, right? We can hear. Can't see real good not because it's not the program's not in there. The programs are in there. It's just our eyes are not developed yet, right? We can breathe, right? I understand. Our heart beats. We can get rid of waste. We're born knowing how to do that, and plus move around. So that's what ROM is. So a computer. If a computer can computer can do only one thing, what can that processor do? It can only do one thing. What's the one thing it can do? It can run a program. Period. So by George, when you turn a computer on, it's got to go someplace. So every time you turn it on, that computer is born. And it's got to have programs that's available that's not in a volatile memory, that's someplace that can't be changed. You get a doctor that gets in there and starts screwing around with your autonomous nervous system, that's going to screw you up, right? You understand? Either you're going to go blind or your heart stops or something like that. So that's what the ROM is. The ROM contains a basic operating system we call the BIOS, Basic Input Output System. Have you ever heard that term? That's the BIOS. It's in there. It's in ROM. Set in there, so that means I can turn this thing off. Batteries can go dead, right? You understand? I can pull the battery out of the dang thing. I can take it apart and put it back together. I plug that ROM in there, and those programs are in there. Next time I turn it on, that CPU knows one thing, and that's every time you start it up, it goes to here. It goes to an address right there. I could tell you the address, but and from then on, it's what? It's running program. That's what it's doing. But I've got to have ability to change the program. And I've got to have the ability to make the computer have more than a basic operating system. So we add to our operating system our whole life. I'm still adding to my operating system. Every time you learn to do something, and now you got it, right? You understand that's your operating system. Computers couldn't do that because what we do is we store the operating system in this right here. So up here we have a basic operating system. Here we got the main operating system. Now how does it get in there? Well, there's a program in here called the boot sequence where it tells it to go to a hard drive or some mass storage device and load the operating system into RAM. Now what's nice about that is that now we can upgrade operating system. So if the operating system was built in ROM, like cell phones were for years, you couldn't download updates all the time. Right? You understand that? Which is pretty neat. So everything's got an address. So all this has got addresses. So what we do to get to peripherals, these are outside of the computer, is we go through a port. And then the peripheral connects to the port. And so the CPU, so this port has an address. So we looked at those IO addresses the other night, right? You understand that? So anytime the program calls for something from your hard drive, it say, okay, I need something from here. It's inside a program. The program will put the address. It would enable the port. Now the port would give it the right timing so it could input information from what? From this slow I/O device into the what? Into the memory or wherever it's going to. So a portal is just where we connect peripherals. So these guys are called what? So these guys are called peripherals because they're on the outside. They're part of the computer, but they're on the outside, right? They're outside. So anything that communicates with a computer through a port is called a what? So this keyboard is not connected to the address bus. It's not connected to the data bus. It's connected to a what? A port. So I come up here and start typing. I can type with one finger per second. I can type real fast. 60 words per second, but 60 words per second is still an eternity to a microprocessor. That's like we're clipping on in gigahertz, So this is the basis of a computer. So we have a basic operating system that does what? Gets it going when you turn it on. Then a program inside here tells it to load the main operating system off a mass storage device. This comes in here and loads that main operating system in here, and the operating system loads off RAM. Well, what happens when you turn your computer off? Well, the operating system's dumped. RAM is what we call volatile memory, except in your phone, by the way. So volatile memory means on these main computers, if this guy right here dies, then you lose everything there, but it's no big deal because why? Next time you boot, it's going to start running here, and then what's it going to do? It's going to just load it right back into RAM. And so these are disk-based operating systems. So that's basically what laptops and stuff like that run. They run a disk-based operating system. Of course, more of your laptops are moving to solid-state drives instead of the hard disk drives. Huh? Solid-state, we have a type of memory. So this ROM has evolved. First of all, ROM was read-only memory. Now the problem with ROM is you bought the programs with the programs in there. And so if your ROM ever went bad, you would have to have somebody make these things for you. So they were made with the programs in there, which made them very expensive. So what they did, they came out with a device called a PROM. And with a PROM, it had thousands of little fusible links in there. And what we could do is we could put it in a programmer, and we could we call it burning, and that burning a PROM. That's what we did. But the problem is, if you screwed up, what'd you do? Took it out and threw it away. Because once you blow a fuse inside a little old tiny chip, you can't get to it. But it gave us the ability to change the program. It gave us the ability to mass produce these things. And then if I wanted to change it, I could change over very, very easy, right? You understand, without doing what? Without having a new mask made. Then they came up with something called an EEPROM. And I'll show y'all some of these. EEPROM, but you couldn't erase them. So once they were programmed, you had to throw them away. An EEPROM was made out of a semiconductor that if you exposed the semiconductor to high intensity ultraviolet light, it would wipe out the ROM. And then you could reprogram it, but you was programming it electrically. So this became known as erasable programmable read-only memory, which is really neat now. So now somebody could send me the code and I could burn a PROM. And I can show you some of these. So you've actually got a little quartz window at the top of the dang thing, so you can look down and you can actually see the wafer in there, which is pretty neat. And then they came out with EEPROMs. Have you ever seen one of these? Oh, yes, you have. I don't have one on my belt. These are our little USB thumb drives. These are EEPROMs. Oh. These are electrically erasable programmable read-only memories. Now, the problem is that it takes a long time to write on them. Have you ever noticed that when you store something on your USB drive, it takes a lot longer than once it's on there, you get it off a lot faster. So and these are solid state memories. So, yeah, well, for one thing, it's serial. It's a serial technology, USB 3 or 2. It depends on what you buy. So we got 3 versions of USB that we went over in class the other day, right? I don't think they've came out with a new version. So these are the standards we have right here. So right now we're setting at USB 3.0, which gets us up to 5 gig. Now this is read. This is read speed. It's not write speed. It's not write speed, because every time you write, what's the first thing it's got to do? Erasable, electrically erasable, programmable. So that means you got to do 2 things before you write. You got to erase what's there, and then you got to write new data in there. When you read from it, you just do what? You read from it. So basically, it takes about twice as long to write than it does to read. So the problem with solid state drives is right now there's no way in the world they can match the speed of actually hard drive. We got hard drives out there running at 7,200 revolutions per minute, and there's like about 36 sectors on there, and so we're talking about screaming devices. These hard drives we have now. Solid state though, these guys are little old tiny things. So the biggest trend for some reason is people want thin. Have y'all looked at something like some of the tablets and some of the laptops now? They're extremely what? Thin. Yeah, it does with all. There's really no mechanics in the thing, so it's all electronic. So that depends on what type. So still, if you get the high end laptops, then they're still going to have what in them? They're going to still have little hard drives in there. If you get low end, the lower end, then odds are, especially if you get a tablet, that's going to have a solid state unit, which is nothing but EEPROM. So it's just these USB drives, but now instead of you plug them in the side where they're at, they're non-volatile, so which real neat. The problem we have though is the read-write time. So a lot of your phones, that's what they use. They don't have RAM in them. They've got solid state. Well, that's not true. They got a section of it is solid state, which would be your hard drive, and then it still has RAM. So if you turn something off and if you turn your phone off, or if the battery actually goes dead, then that's probably in RAM. Any more questions? These are good questions. So that's why. So this would be a port. So everything in the computer. So this guy right here would be assigned an address, and it would connect to the microprocessor's bus. And then over here, this would be the port that's inside the peripheral. And parallel would be the fastest way we could possibly send data. But what you got to understand, once I get to on the other side, outside, then speed is no longer, because you can't run faster than, you don't need to have a port that runs 10 times faster than any hardware you could possibly have. So how fast would the port have to run on my keyboard? How fast can you type? Huh?
Not very fast.
Yeah. So there's no need of using parallel for the keyboard because there's no way in the world. We don't USB. That's a serial port. That's because we do that because of price, right? You understand? Serial ATA is a serial port. It's a hard drive port, but it's serial ATA, so it uses differential. It's a high-speed drive. We could do it faster parallel, but there's no need to do it faster parallel because there's no mechanical hard drive that can keep up with the parallel port. Does all that make sense? So parallel, we still run into parallel. You're going to run into it, but when you get into computers, as far as on the outside world now, coming out, just about everything's what? Just about everything's serial, except for HDMI. It's a little different. Your video is still parallel because it's such demanding. Are we okay? These are some of the parallel ports. Digital has been around for a long time. And we dealt with digital or before. I mean, we dealt with logic before there was any such thing as logic gates. When I worked out at U.S. Steel, we had some NORPACs out there, which was the first digital logic that I actually ran into. There was no PLCs out there. Everything was done with relays. Well, if we're going to do logic, then we're going to have to do it with other things besides logic gates. We have some logic operations. Anybody know what the logic operations, the basic logic operations are? We have what we call an AND, or good. Yeah, we have what we call a NAND, then we have a NOR, and then we have what we call a NOT. And this is it, guys. So all digital logic is made out of these five. These are what we call the 5 basic functions right here. So if I can understand these, so if I come over here and we're going to draw this like we do in motor control, so it's so easy. So this would be plus, this would be minus. We'll use DC. And what I'm going to do is I'm going to come over here and take some mechanical switches. These are the symbol for switches. Single pole, single throw switches. And over here, I'm going to come over here and I'm going to put a light bulb. These are nothing but switches. So when does the light come on? So I'm going to call this 1, and I'm going to call this 2. Well, let's use one of these logic terms over here. Let's don't say both. There's no both over here. Which one would those you say? You'd say when 1 and 2 is closed. That makes sense? So this is AND logic. It's been around for years. Well, what if I come over here and do this? So I have the same thing. So this is my circuit between here. Okay. And I come over here and I put a switch right here. And this is a symbol for a light, by the way. And then I come down here and put another switch right here. And I call this 1, and I call this 2. Now we're not going to say either. We're not going to say these are the terms that we're using. Yeah, because you say 1 or 2 or 3 or 4. So you got to understand, I can keep putting control devices in series, or I can put them in parallel. And I could come over here and add one right here, and now we would have NOR AND, right? So we'd say A or A 1 or 2 or 3 and 4. So we've been doing logic for years. So what we're doing here is this is what's required to turn the light off. NANDs and NORs and NOTs are what's required to turn the light on. So these are what's required to turn the light on. Did I say that right? Because I had something else on my mind. So these guys turns the light on. What these guys are going to be what's required to turn the light off. So if I come over and do this, so these are what we call normally closed contacts, switches. So would that be a NAND, or what would that be? Huh? It can't be an AND because the light's already on. So it can't be an AND. So AND says, okay, this and this has to be true to turn the light on. On this one, right, you understand. This is not an AND. This or this will turn the light off. So this is a NOR. Or, so or, right? But here you're saying not, so basically say not on. This or this makes the light not on, so that's a NOR. And this gets people confused because they jump on this right off the bat. Okay, they jump on this right off the bat. So that's a short circuit. So when they see this, they see those things wired in series, and automatically they want to say what? They want to say AND. because they learned it this way, but no, this is a NOR. So what would you think a NAND would be? With normally closed switches. So we come over here, if I did this, that's a normally closed. And then I came over here and did this. This is only 2, but understand I could do this. I'd do this wrong. This would be a what? This would be a NAND. Because this and this, right? You was required to turn the light off. So we've been using logic for a long time. And then we got this one guy that's kind of unique. So to get an or get an and, to get an and, or, NAND, or NOR, you got to have at least 2 things. So what logic is this? This is not logic. There's no logic. I mean, this guy just turns the light on or on. There's no logic there. So we have digital devices we call buffers that we'll talk about later on. They don't do logic, but they got a function in life. This right here would be. So if you got one normally closed contact, this is a NOT. So that's our 5 basic logic functions, NOT and ANDs. So what we got is we got switches. So this is one way we can represent logic, right? So people that's had motor controls, when you take motor controls, when we teach logic, that's what we're going to do. You're going to wire push buttons in series. You're going to wire them in parallel. You're going to wire normally open, normally closed. Y'all understand those terms? So this is digital, but it doesn't do any logic. I mean, there's no logic. It don't invert. It don't take more than one. This does cause something because this actually gives us opposite of what we're looking for. So that's not. We can use relays. So electromechanical relays. And that's what I wanted to show you. I had one out the other night. I put it somewhere when the class got out. Here it is. This is a good one. So anytime we put current through a wire, we create a magnetic field. The Navy is working on something called a rail gun. Do y'all know what a rail gun is? Okay, tell us about it. What is a rail gun? Okay, guys, we okay so far? Any questions? Do y'all know what a check valve is? Check valve. Yeah, we run into them all the time. My mother and dad lived down in a place called, or lived in, they're both passed, Bessemer Gardens, and it down at the way down at the end of the road was Valley Creek. Everybody knows what Valley Creek is. And we had a stream that ran into Valley Creek, and of course it went through a big old pipe there. One time we had a ton of rain, and Valley Creek backed up into Bessemer Gardens. He'd get my mom's house because their house was up on the hill. But I was a kid, and I mean we were going down through there with a boat right on top of a car. So the car was completely underwater. So they came in and put a check valve on there. So the gate was up when the flow was out, but if Valley Creek ever tried to flow back in, what did it do? It closed the check valve. So any technology that uses the flow of something, fluids, we have a check valve. Hopefully you got one in your house. So if power company that comes out there, the water company comes out and cuts off the light, or they get a break, all the water doesn't run out of your house, which is not good because it'll go through your meter. Your meter has no idea which way the water's flowing. All it knows is flowing. So what would it do? It would bill you twice, right? Plus suck all the water out of your house. So you should have a check valve on your water system coming into your house. We have check valves in hydraulics, we have check valves in pneumatics, and we have check valves in electronics, because we have the flow, but here we have the flow of current. So when solid state, we'll show you how these things work. We'll explain how they work. All you need to understand, this is a check valve, and all it does is let current flow in one direction. These devices are called, they're solid state devices, are made out of semiconductors, and this only lets current flow in one direction. So what we have is, of course, in electronics, we have symbols, and I'll show y'all some of these devices. And it don't make any difference how big they are. So basically, we draw a triangle, and it's supposed to be colored in, but a lot of people don't color it in because it takes time. And then we put a bar right here. And then so we have two connections. In electronics, we call these leads. So it's got two leads. This lead right here on the arrow side, we refer to this as the anode. And this end right here, we refer to this as the cathode. The first diodes were made out of vacuum tubes. And that's the way they worked. They had to have something called a cathode, which emitted a cloud of electrons. So when they came over and came with the solid state version of that, they carried the same names for these leads over, of course, so electronic repairmen wouldn't get confused. Well, in tubes we call it this, in solid state we call it that. So that's where the name comes. Okay. What's that? I thought I unfroze it. Oh, it is paused. Okay. It wasn't paused. We were okay. I don't know what the freeze meant. Normally when it's paused, you'll have that two arrows in the center that point both directions. Oh, it wasn't paused. So when we get into electronic or solid state devices, we have something we call bias. And bias is this is a DC polarity or DC voltage that's applied to a semiconductor. To control its operating parameters. And we have two types of bias. We have what we call forward bias and reverse bias. So to forward bias this, what we have to do is we have to point this toward the positive potential, and we have to point this toward the negative. If we do that, then the check valve's open, so current flows through it. So forward bias means the anode has to be more positive than the cathode. It doesn't mean it's got to be positive. It's got to be more positive. So I could have negative on both sides. It's just that if I come over here and this is a negative 10 volts, then this might be a negative 9.3. Huh? I know what I did. I did this. We okay? So I understand what you mean by freeze now. I thought I didn't look up there. So DC voltage applied to a semiconductor to control the operating characteristics. So to forward bias it and make it work, the anode has to be more positive than the cathode. It doesn't mean it's got to be positive. It's just got to be more positive. You understand a minus 9.3 is more positive than what? A minus 10 or less negative. Y'all understand that? And that gets people confused. They say, well, the anode's got to be positive and cathode's got to be negative. And we have people that teach that, but people that teach that don't understand how this thing works. And the main semiconductor we use, and these, when I send water through a check valve, it's going to have some opposition, which means you're going to lose a slight bit of flow when it goes through a check valve, just to operate the valve. So we're using a semiconductor called silicon. And a silicon diode, we have a rating called VF, which is the forward bias voltage drop, and it's equal to approximately 7/10 of a volt. Now it varies with current. So the more current you have flowing through it, it's going to drop a little more. The less you have, a little less. But you'll find out 7/10 of a volt works out real well for silicon, and they're the predominant diodes. So if I was to come over here and make this negative and put this toward the positive potential, then it cuts off. So we use these things for all things because they only let current flow in one direction. AC, how does current flow? Two directions. But I can use diodes, and if I know how to hook them up to an AC circuit, I can take AC and make it only flow in one direction on the other side of the diodes. We call these rectifiers, by the way. If you ever heard that term, rectifiers, that's what they do. That's all they do is they're check valves. We bring AC into them, we get DC out of them. And when you take solid state, some of y'all are taking it, I know Pavana's taking it and Joseph's taking it. That's one of the things we talk about is power supply. But they learn how the diode work. We just tell you here what they do. So reverse bias, if the anode is more negative than the cathode or less positive, right? You understand, by 7/10 of a, not even 7/10 of a volt. 7/10 of a volt when it's turned on. When it's turned off, it's just off. Okay, y'all understand that? So it only lets current flow in one direction. So we can do logic with these things. But now instead of using relays or using switches, this is solid state, so we're letting electronics control electronics. No electrical mechanical parts. So here's some diodes, guys. I couldn't find my in-betweens. By the way, these are diodes, and you can tell the anodes from the cathode. So the cathode has the bar, or has the circle around it. In fact, we got enough of these for everybody. I need to bring them back to them. Make sure I get them back. These are diodes. And of course, what determines the size of the diode is how much current it's going to have to control, right? So the more current it's going to have to control, the bigger the diode is going to have to be. The less current it's going to have to control, the more it's going to have to be. So I can look at this one, that one you got right there, and then I can look at this one right here, and I can tell that that one right there can control more current than this guy right here. Now it's not going to focus, but I don't know if you can see it or not. Maybe I can put it against something white. Sorry, rip it off here. Yeah. See the black line right there? Can y'all see one lead is black? So that's the cathode. And then the other lead would be the what? Would be the anode. And this is a diode, and it's going to only let current flow in one direction. What happened to my lead? So, by the way, you can't check this with a regular ohm meter, and we call it an ohm meter, even though it's going to display in volts. But just about every one of your newer meters has the ability to check diodes. So you have a well, it actually checks what we call a p-n junction. So you can use this to check all kind of things. But what they do on your meter is the scale that you use to check these things is going to have the little symbol of a diode on it. So you really got to honor polarities on this thing. So here's my diode scale. Right here. Can you see it? So it's got the little symbol of a diode. And then it's also your continuity check. What's continuity? Anybody know what continuity is? Continuity is a term we use in electronics to indicate a path that's got almost zero opposition. So we use continuity all the time to find wires. So I'm trying to figure out where a wire goes. Well, the easy thing to use is to use your ohm meter, right? But the problem is you got to look at the meter. So it's got a continuity checker on it that when it sees less than a certain ohm level, it comes up and beeps at you. So now all you got to do is go and put this lead over on this side and touch that on. If it's a straight piece of wire, can you hear it? And so you don't even have to do. So we find continuity all the time, checking fuses. So fuses have very low resistance when they're good. They have infinite resistance when they're bad, right? You understand? So we check a fuse. We check fuses all the time. So y'all need to get used to checking fuses. Check circuit breakers. We can check anything that tries to break the circuit. We check a switch to see if it's good or bad. We can use our ohm meter. But if we use a continuity checker, we don't even have to look at it because this tells us when we have less than a certain amount of ohms, right? You understand? So if I wanted to check a fuse, which is basically supposed to be like a lot like a wire, then I can come up here and I can just, so I know that wire's good, right? You understand? And we trace wires all the time. Most meters now, most of your new meters, when you open it, when you put it on the diode scale or the continuity scale, it's going to show overload. This meter is a little different. What I'm going to do is I'm going to check a diode. And what's nice about this is, so I'm going to come up here and I'm going to take my red lead and I'm going to put it on the cathode. And I'm going to take my black lead and put it on the anode, and it shows me the same thing it shows me when don't even have it connected. So this is an open, right? You understand? I'm going to come up here and put my black lead on the cathode, and I'm going to put my red lead on the anode, and it shows me about 0.6 of a volt. Oh, y'all can't see the last digit. So this means this diode's good. But look, it only measures when I forward bias it, right? You understand? When I reverse bias it, it gives me the same thing it gives me when I'm not even touching. So this is an open, right? So now it's an open, right? So now it's acting like an open. And now it's acting like a closed switch. It just drops a little bit of voltage. A closed switch will drop 0 volts, right? You understand that? A solid state device will never drop 0 volts because it's not a closed switch. This only drops about 700 millivolts. That's rule of thumb. Notice this guy dropped about 600 millivolts. But 700, what's 100 millivolts between frames? And this is with your meter. So that's pretty neat. So this is the way we can check what we call a P-in junction. Transistors have diode junctions in them. FETs have diode junctions in them. So you can use this scale on your meter for a lot of other things besides checking diodes. This is a diode. It's a stud mount diode. If you look around real good, if it focuses in, here's the diode symbol right there. See it? So this is the cathode, this big old stud right here, and this pigtail right here is the anode. Can I check this with this ohm meter? Sure, it's a diode. So I'm gonna come over here. I'm gonna put my black lead on the cathode. Okay, so it says this is the cathode. I'm gonna come over here and take my red lead and put it on this guy right here. That's the anode, and there it is. I come over here and reverse that, and it stays the same. See that? So I know that this guy right here is good. Well, look at that sucker. That sucker's probably rated at, I don't know how many. We could look it up. Probably about over 100 amps. But it's a check valve. So if I need a check valve for 100 milliamps, I'm gonna need check valves for 500 amps, right? You understand? So what determines the size of the diode? Well, it's nothing but the size of the diode depends on how much current it can actually cut off and how much current it can cut. So y'all, if you got your meter, you got that diode scale on there, and you can check these things. And not only, and of course, when you get into solid state, we'll show you how you can use this to check transistors. You can use it to check FETs or bipolar transistors. It's a neat little scale on your meter. You check it on the scale that's got the little diode on it. See the little diode symbol on there? So yeah, you can play around with your meter, to flip it on, and try to check one of them, which is pretty neat. But what is digital? Digital is off and on and off and on, right? You understand that? And these guys turn off and on and off and on. To make them conduct, we got to have at least 7/10 of a volt on a silicon. We got to have it forward biased by at least 7/10 of a volt. And when I say at least 7/10 of a volt, it don't drop any more voltage than that. So you got to be real careful. If I came over here, let me find my blank slide again. So if I was to come over here like this, and I put my diode right there, and then I come over here and put this across my car battery like this, what would happen? It'd blow that diode just like that. Because once it's forward biased, it is a closed switch. So anything above 7/10 of a volt would be a short circuit. Y'all understand that? So what would we have to do? Well, we would have to do what any normal person might. We'd have to put a resistor in here somewhere, right? In series. Now we're okay. I'd have to size that resistor for the current, but now it's forward biased, and this resistor, if this was 12 volts, this resistor would drop approximately 11.3 volts, and this guy right here would drop about 0.7. So don't ever put a diode across a voltage source. Okay, everybody, we gotta have a resistor to protect it, right? Everybody understand that? So let's see if we can do logic with this thing. Let's see if I. Okay, so relays. Okay, diode's the perfect switch. Okay, so here we go. So I'm gonna draw these out. See. Well, look at the symbol. No, here's the symbol right here. There's the symbol right there. This is the cathode. Oh, you wanna? So what I'm gonna do is I'm gonna come over here. If we're gonna do an AND or an OR, we gotta have at least two inputs, right? Everybody understand that? I'm not gonna color these things in, even though they're supposed to be. So I'm gonna put 3 of them up here. Now, when we're dealing with logic, we're dealing with what we call ones and zeros or highs and lows, right? You understand? So what I'm gonna do is I'm gonna come over here and I'm gonna put a resistor right here. And I'm gonna take my output right here. So I'm gonna come over here and I'm gonna put my meter right here. And what we're gonna do, of course, over here we'll put 5 volts or we'll put 0 volts. And 0 volts is not a nothing. 0 volts is a ground, right? Or common. Okay. And we're gonna say 5 volts is going to equal to a 1. Well, actually it's gonna be 4.3 because the diode's gonna drop 7/10 of a volt. And we'll say 0 volts would be equal to 0. Okay? Okay. So I'm going to come over here and we'll come over here and we'll put so these guys have been around for years. And anybody says that they're not still used, that you don't understand digital, you'll run into these a lot because they're very simple. I can control how many inputs we have. So if I go out and buy a logic gate, you're gonna be set by the number of inputs that's inside that integrated circuit, right? You understand? This, if you wanted 15 inputs on this, you could use just 15 diodes. You can buy diodes, by the way, in integrated circuits. We'll talk about that. Okay, so let's say I come over here and I put zeros over here. What's the output going to be? So what I'm doing, we're going to come over here and we got 3 inputs. And let's call the inputs, we're going to give them names. We're going to call them A, B, and C. And then we're going to call the output Z. And I'm going to come over here and start writing. How many combinations can I put on the input over here, by the way? How many different combinations can I put on that input? How many inputs do I have? I have 3. Each one of them I could start counting, right? So I could put that input on there. I could put, that would be an input, right? 2, right? 2, 3, 4, 5, 6, and 7. That's all. I can't put any more. 1, 2, 3, 4, 5, 6, 7, 8. So you can, on a digital logic gate, you can tell how many input combinations you have. Just count the number of inputs and raise 2 to that power. So how many inputs do we have? How many inputs do we have? Not combinations. How many inputs do we have? 3. Okay. Each one of them takes 2 combinations. I have 3. That tells you right off the bat how many combinations you can put on there. No more, no less. So this is the first one we're putting on here. Here's A, B, C. So I've got all zeros. What would Z be? I'm gonna put Z over here. Would it be a 1 or would it be a 0? Got to be a 0. I mean, where's it gonna get a 1 from, right? You understand? And that's the purpose of this guy. So what the purpose of this guy is what we call a pull down resistor. How much voltage does a resistor draw? Ooh, that's a question. How much voltage does a resistor draw? So let's say this is a 1K resistor. How much voltage does a 1K resistor draw? Huh? How much voltage does a resistor draw? V is equal to, it's not equal, V is not equal to V. What's V equal to? Ohm's law? Okay, so if you have no current flow through a resistor, it drops no voltage. If it drops no voltage, that's effectively bringing this and putting it right there, right? You understand that? So that it's dropping no voltage, so it's acting like a piece of wire. People don't understand that, and that's why when you're troubleshooting, if you got an open resistor, all the voltage drop is across the resistor. Why? Because nothing else is dropping any voltage. Why are they not dropping any voltage? Because there's no I. You got no current. So everything else is acting like a straight piece of wire, right? Okay, so that's good. So let's see, what would we get out now? So let's go come up here. Let's put in our next combination. So I'm going to put a 1 on A. So I'm going to put 1. I'm going to put 0, 0. Now, when we say a 1, let's don't say a 1. Let's come over here and actually put the voltage level. So what are we putting in over here? What did I say? We're going to put plus 5 volts. So here I'm going to put plus 5 right there. Here I'm going to put 0. Here I'm going to put 0. So is A on or off? Is the cathode pointing toward ground and the anode pointing toward power? It is, right? So is it on or off? Okay, it's on. Is this guy here on or off? It's off. Why is it off? Because it has no potential. It is not biased. It's got 0. It's looking at 0 on both sides. Just for now, of course, what's going to happen is this guy's turned on, so it's going to let voltage come through. What would I get out? Well, I'm going to get out approximately 4.3 volts. And why is that? Because the diode drops about 0.7. Now, as soon as this guy here turns on, that puts a positive 4.3 on this cathode, 0 on the anode, so it's turned off. Why would this guy be right here? Off. So this guy right here goes to 5 volts. We got 4.3 volts out. So we're going to put a 1 over here. Right? Everybody okay? So what are we going to do next? Well, what we're going to do next is we're going to come over here and we're going to stop doing it. We're going to go down the chart in a minute. I'm going to come over here and I'm going to put 0 volts right there, plus 5, 0 volts right there. So what happens now? A does what? Yeah, A turns off. Yeah, so A turns off. B turns on. C turns off. So we get 4.3 volts now. So I'd do what? I'd put another 1 there. Okay, so what's going to happen next? On the next one, both A and B is going to turn on. What are we going to get out? We're still going to get 4.3 volts. We can't get more out than we put in, right? Y'all understand? So what would we get? Somebody tell me. So on this combination right here, what would we get? We get a 1. What would we get here? We get a 1. What would we get right here? We get a 1. What would we get right here? We get a 1. What would we get here? We get a 1. So what do you think logic is this? Is this AND or is this OR? I can't do NAND and OR with this yet. I'll show. Well, we can't pick up a NAND and an OR until we pick up another device. So this is an OR. This is an OR gate. So if A is high, or B is high, or C is high, we get. Now the term we like to learn is any. So if you come up here and you use the term any, that's OR. So any high gives me a high. Or any 1 gives me a 1. That make sense? Is that cute? So here's a logic gate, nothing but diodes. This OR gate. No moving parts, solid state, operates at the speed of the diode. We get these little switching diodes, these guys right here. So odds are this gate would be made out of these little guys right here, not those gray ones. So those black ones are what we call rectifier diodes. Those are designed to, those have a slower switching speed. They're designed to turn AC into DC. These are called small signal diodes or switching diodes. These guys are not designed to handle a lot of current. We don't need a lot of current because we're doing logic, right? You understand that? These guys here switch at an astonishing speed. You just wouldn't understand how fast these other guys can switch. If this was a relay, I could do this with relays, right? You understand that? I mean, I could do this. I could hook up 3 coils. Then down here, I could put a contact and get an OR on the light back there. But you know, now we got electromechanical devices. We got a lot more cost. Some of these guys right here are going to be down in the pennies, right? You understand? You ain't going to ever find a relay for that price. So not only are we switching at a lot faster speed, but we can't change the level of the voltage. So these guys don't do away with relays, but it takes the place of the logic, right? You understand that? And that's what a PLC does. So PLC does not do away with relays. What it does is it does the logic. It does the part that don't require a lot of current. And then when you need a lot of current, you use a PLC to do what? To pick up a relay and let the relay give it the current, which is exactly what your car does. So your car, the electronic control module in your car is a lot like a program controller. Some things it can control. It can turn on little lights on your dashboard. It can do that. But it cannot turn on your headlights. So what does your ECM do? Well, it outputs and turns on a relay, and the relay turns on it don't turn on your air conditioner. It outputs output to a relay. Your relay picks up your compressor, right? You understand that? So we're not doing away with relays. PLCs do not do away with relays. It just takes care of all that ands and ors and nots and nands and nors. That's what it does for me. So instead of me using relays to do the logic, now I do solid state to use the logic, right? You understand that, which is pretty neat. These guys couldn't turn on a relay either, but when we add one more component, we could see we could do this pretty easy. Okay, so this is an OR. Solid state, no moving parts. As long as I didn't wipe this out with a big transit voltage or something like that, these guys would operate forever. We give a little protection to them. PLCs are really protected. They're really, really rugged little boxes. Y'all seen PLCs? We'll go over and look at the line in a minute. So let's redo this. Instead of doing instead of using 3 inputs, which gives 6 combinations, we'll make a diode gate that's only got 2. So that way we only got 4 combinations. So notice this time I'm going to turn the cathodes toward this way. So I'm going to input on the cathode. The other time I input it on the anode, right? And instead of putting a resistor that pulls it down the ground, what I'm going to do is I'm going to come up here and I'm going to put a resistor up here that pulls it up to voltage. So a resistor that pulls it down to ground or common, we refer to that as a pull down resistor. One that connects up to power or voltage, we call that a pull up resistor. Does that make sense? Okay, so we'll call this A and we'll call this B, and we'll take our output right here. So I'm going to hook my meter right here. I'm going to connect this to plus 5 volts. Okay. So A, B, Z. By the way, we call this right here, we call this a truth table or a function table. So if you ever heard that term, that's what it is. 0, 0, 0, 1, 1, 0, 1, 1. So that's the only combinations we can put on this. Truth tables are okay as long as you're dealing with up maybe 4 inputs. You start getting to five inputs, and you have 32 combinations in your truth table. You know, 6 inputs, you would have what, 64? So truth tables are okay as long as the input. But it works good to see that the operation of these games. Just a very few inputs. Okay, guys. So I'm going to come up here and I'm going to put a 0. I'm going to put a 0 and a 0 right there. What would the output be? It's going to be 0, yeah, and that's one of the resistors got to be there. So this guy's forward bias. It's going to drive. Well, actually, it's going to be about 0.7 volts, but it's still going to be considered a 0, right? That would even be legal in TTL. TTL, anything above 800 millivolts is considered to be a legal 0. So I'm going to put a 0 right there. Okay. Good, guys. So I'm going to come up here now and I'm going to make I got it backwards from a while ago. So I'm going to make A a 0 and I'm going to make B plus 5. What would the output be? This guy's turned on. When it turns on, it's effectively bringing this 0 and putting it right there. Actually, it'd be a 0.7. So that's going to put a 0.7 right there. So now the cathode is positive in respect to the anode. So this guy right here is going to turn off. It's still the same. It's just that we turn the diodes on. Yeah. I mean, it's still the cathode has to be negative in respect to the anode, right? As soon as this guy here turns on, the 0.7 of a volt, that puts 0.7 right there. That puts plus 5. Is the cathode negative in respect to the anode? No, it's positive. So what's it going to do? Okay, so what's this going to give me? It's going to give me a 0, right? Instead of putting plus 5 in 0, let's go ahead and put 1s and 0s. So we know 1s are plus 5 and 0s are grounds, right? So my next combination, we're going to make A a 1, and we're going to make B a 0. What would the output be? Same thing. Now this guy right here does what? This guy turns on, and this guy does what? Turn off. Okay. So I'm going to come up here now, and I'm going to do this. Now, okay, what's going to happen? This guy's going to turn off. This guy right here is going to turn off. What's the output going to be? Well, now there's no current flow through this resistor anymore. So every time from now on, we've got current flow. Now there's no current flow through that resistor. So how much voltage is it going to drop? Huh? It's going to drop 0. So that means if 5 volts is right there, this guy drops 0, what's going to be right here? So I'm saying 5 minus nothing is equal to 0. Gee. It's dropping no voltage. Yeah, that's the problem people don't understand. It is dropping no voltage. If it's dropping no voltage, so here's my voltage drop right there. It's dropping no voltage. So 5 minus 0, is that 0? Okay, so the output would go to plus 5 volts. So both these guys turn off. For some reason, people say when the guys turn off, the outputs go to 0, but that's not true. So now we have no current flow this way. Before we had current flow this way, right? You understand? This was 0 volts. That's 0.7. This guy has been dropping 4.3 volts because there's been current flow through it. Kirchhoff's voltage law says the sums of the voltage drop in a series circuit has equal to applied voltage, but that's only if you have current flow. Okay, right? You understand? As soon as I come up here and do this, what do both these guys do? They turn off. Now we have no current flow through that resistor. If we have no current flow, it drops what? It doesn't drop 4.3 volts anymore. What does it drop? Drops nothing. What does the output do? It goes up to plus 5 volts. So what logic do you think this is? Anytime we use this term right here, this is going to be some type of AND. Anytime I use this term right here, this is going to be some type of OR. Which one will they use here? I'd say all highs to get a high. A while ago we said any high to get a high. Here we say all highs to get a high. So what logic is this? This is AND. So we can't invert. We can't get a NOT with diodes, by the way. We can with another device that we'll have to look at, which is pretty neat. We'll have to add a device called a transistor. And how many of these diodes can I put to get this AND? I can put as many as I want, right? Y'all understand that? So if I needed a 15 input AND gate, I could just get 15 diodes. So here's the logic gates right here. What's the one on the left? Huh? Now this is an AND, and this is a. One more thing we got to get through. This is called a bipolar transistor, and we're not going to learn. We're going to learn what it does, but we're not going to learn how it does it. Solid state, y'all learn how it does it. Here we're just going to learn how it does it. So what a bipolar transistor does, and we got FETs too, by the way. We have two types. We have NPN and PNP. The most popular is the NPN. And this is the symbol we use to represent it. We have 3 leads. This is called the base. This is called the collector. And this lead right here is called the emitter. Now, a diode is a check valve. What can we do with a regular valve? So I've got a valve on my sink in the house. What can I do with that valve? I can turn it on and I can turn it off. Or I can also control the flow. So I get 2 places. I can either turn it all the way on, or I can turn it all the way off, or I can put it in the center and actually control the flow. This is what a transistor is. It's a current valve. We can operate it as a switch, which means we turn it wide on, or we turn it off. Or we can operate it as a rheostat, which is this is where we use it as in amplifiers. So these are your amplifiers. You don't operate it in what we call, so we got 3 places we can operate it. We can operate it in saturation. So that means you've got that sucker turned wide open. So when we saturate it, it acts like a closed switch. Now the switch is between the collector and the emitter. So here's our switch right here. This, the base, is what we control the switch with. So this would be like your wall switch. So you would be the base. So you go over there and you flip that switch, you're the base. Of course, you do this mechanically, right? You understand that. Here we're going to control this switch electrically. So we got cutoff. So this is when we turn the valve off. Here it acts like an open switch. And the other one we're not going to use, we call it the active region. This is when it acts like a rheostat. but you're controlling that rheostat electronically. So instead of you turning a knob up there, these are your amplifiers. So all your amplifiers operate the transistor in what we call the active region. We're not concerned with the active region. We're concerned with this guy right here. So if I saturate it, I get almost zero resistance between the collector and the emitter. When I cut it off, I get maximum resistance between the collector and the emitter. And these guys are solid state. These are not relays. These guys can switch extremely fast. Now, how do we do that? Well, we got to bias it. So what's a bias? What's bias, guys? It's a DC voltage we apply to a semiconductor that tests its operating characteristics or its parameters, right? Have y'all heard that before? I know it's time for a break. So what I have to do to forward bias this is a symbol, and what you do is you look at this guy right here. Is it pointing in or pointing out? The arrow, is it pointing in or pointing out? Okay, so we got these right here. So, I'm sorry, it's all the same symbol, Rich. We got two types. And notice these are the two symbols we got. So we'd say this is not pointing in. So this is the symbol for what we call an NPN transistor. This guy right here is pointing in, so this is a PNP. Predominantly we use NPNs. Okay. So what do you think the P means? Positive. So that means I have to make the bait positive in respect to the emitter. So the emitter has to be negative in respect to the base, or vice versa. Now this is where this gets confusing, and we're not going to talk about why. We have to make this guy positive. The collector has to be positive in respect to the base. So notice here I put a little old tiny plus. Up here I did put a what? Big plus. So if I was going to do this, let's say I wanted to use this to turn on a light bulb. Well, what I would do is I would come over here and I would put my light bulb right here, and I would connect my positive supply right there. And then I would come over here on my emitter and I would connect this to common. Understand that? Okay. So right now it would be off. Why? Because there's nobody over there flipping the switch. We got to have a base. So what I would do over here, we got two options. Right now we'll just come over here and do it this way. Because I'm going to put a resistor there, and then I'm going to come over here and say we put a push button. And then we'll come over here and connect this plus 5 volts. Now you're mechanically doing this now. So what would happen right now, we have no polarity with the push buttons up. We have no polarity on this. And this, by the way, what you need to do is look at this as a little diode up there. So that means, and it's made out of silicon, so that means it's going to drop about 7/10 of a volt, right? You understand that? Anything above 7/10 of a volt would be a short circuit. So that means I've got to have that resistor up there. If I came over and put 5 volts in directly and pressed the button, the transistor would pop just like that. So that's our little check valve. So I come over here and press this button, then what's that going to do? That's going to put at least 0.7 volts right there. This guy's going to drop 4.3. Then the light bulb's going to come on. Then I come over and let the button go, and it goes up. Now, what we get out of a transistor is that the base current is almost nothing, and the emitter collector current is real big, so we get what we call a current gain. And we call this the beta. So a transistor has a rating of a beta. The transistor we're going to play around with is a 2N3904, and this has a typical beta of about approximately 100. So that means if I press that little button, I'm putting 1 milliamp into the base. I would get 100 milliamps over on the collector emitter. So this is the big advantage of a transistor, is that we get a mechanical gain. It's just like your valve. So you go home and turn your water on your faucet and try to stop the flow of the water with your hand. Can you do that? No. But you can take that little valve and you can turn it, and now you can cut it off and cut it on because you get a screw advantage on that. So you get a mechanical advantage. So here we get an electrical advantage on the transistor. It takes a very little base current to control a big, we call it collector. We ignore the emitter, a big collector current. But, you know, if we know the collector current, the emitter current would almost be equal to that. We're not going to explain that. The biggest current flow in the emitter, the biggest current flow in the transistor is the emitter current, because the emitter supports the base. But, you know, so if I'm getting 100 milliamps up here, then we would have 1 milliamp going that way. Down here we'd have 101 milliamps. Up here we would have 100 milliamps because we have 1 milliamp worth of base current. Does that make sense? So for all practical purposes, we say that the emitter and base are, the emitter current and collector current is equal. And these guys right here, so look. So let's come over here and do this. Oh, y'all take a break, because this will take a little while. What time is it? Yeah, we're going to